I'm delighted that we have our final guest speaker in this course, Niloofar Mireshghallah. She is a postdoc at the University of Washington, and before that, she was a PhD student at the UC San Diego. She's working on topics in trustworthy machine learning and NLP, and she has received numerous awards and fellowships for her work. And today we will hear a little bit about what she has done around privacy and memorization in large language models. All right, so take it away. We are now all remote for this lecture, and I think it's best if you take questions along the way, but it's up to you. And I will help you with checking the chat and reading the questions for you.
Great. Thank you. Thank you so much for the introduction, and thank you so much for having me. And it's really nice to see you again, although remotely, but
Yeah.
and I'm so glad to be here. Okay, please feel free to interrupt me at any point. I love, or like even disagree. And I like a good chaotic kind of environment. That's how you get ideas. So yeah, feel free to stop me. And one question, the audience is more NLP, right? I just want to know like where to go deeper in the background. So the NLP background is probably, or yeah.
Yes, so we have covered in this course large language models, everything from pre-training, instruction to fine-tuning, RLHF. We talked about efficiency like QLoRa, and more classical NLP stuff is what we will hear at the end of this course. So students haven't heard about tasks like part of speech tagging or named entity recognition yet, but they have heard about tasks like machine translation, questions answering, and summarization.
I see, I see.
Any
You
other
already know more
questions?
than
Sorry,
no,
second.
no. I said you already know more than I do, so it's great.
We'll see after the final exam. You can take it. You can compare.
No, I'm on the job market. Don't do this to me. I have a reputation. I need trouble. Okay, great. Well, yeah, thank you again for having me. Also, it's my birthday today, so I'm gonna be giddy. But
Happy
cool.
birthday.
Thank you.
Happy birthday.
Oh, thank you. Okay, I'll start. But again, feel free to interrupt me at any point if anything doesn't make sense. Great. So I'll be talking about membership inference, contextual integrity, and all of that in the context of language. So I'll tell you what all of those mean. But the main thing is that we're going to be talking about privacy and language. Okay, let me start. So we've all, at least here now, we've established that we all know what LLMs are, and we all deal with them. A lot of us use them on a daily basis, right? People use ChatGPT, some people use Claude. I'm not getting paid for this, but use Claude. Claude is better. Just personally, I don't know why, but I like it a lot more. It's kind of more creative. I don't know. But then most people use ChatGPT, so you guys know what these are. And yeah, what they do basically, well, they're much more complex with the scale, but basically they're doing next word prediction, right? So how they're pre-trained is given a context, what is the next word, and then they model the probability mass. And in terms of the practicality of the training, they're just trained on whatever you can scrape from the web or anywhere, throw it at whatever large of a model you can, and then get as much compute as you can, and then you keep training. So that's basically the basics. So that was the math of it, and then this is the scale part of it. Now, why are we caring about them more? Like, why is it that people are caring, and especially about safety? Suddenly, safety and trust is becoming a bigger issue. Why is that? The main reason is, and I feel like we as researchers, we tend to maybe undermine this, and we've kind of gotten numb to it, but it is a huge deal. There was this thing that was a research artifact mainly, right? Like GPT-3, when it was released, it was something that researchers we use that with an API access, and then it turned into GPT 3.5 Chat GPT. But then suddenly this research artifact became a user-facing product, right? Lay people are now using it. Like everyday people know what this is. So something that we were just doing research on till like yesterday, the next day it became a thing that everyone knew about. And like there is this 180 millions monthly users for ChatGPT is a bit of an old stat. It is around 200, and even in September it peaks to 400. Do you know why it peaks in September?
School
Cool.
start?
Yes, cool. So it peaks,
Yes.
so and it might even be more, yada yada. So there's a lot of people who are using it. And in fact, ChatGPT was the second fastest growing application, which reached 1 million users in less than 5 days, only second to Threads, which I actually don't consider Threads a real thing, because they made people sign up to Instagram something something. So I would say that it is probably the fastest growing application. So a lot of people are now using it, and that's why we care so much. And what makes this model or like ChatGPT, Dolly, all of these good is the scale of the data and the compute, right? So we're using a lot of data to train these models. But then one thing that happens is that as these models size up, their propensity to memorize their training data is also expanded, right? So they're likelier to memorize, and then they're likelier to regurgitate the data. And again, a lot of times things like we talk about things and you hear like, oh, this data was extracted from ChatGPT, and it kind of sounds like this is a new problem, or it like, it fell out of a coconut tree, like there's no context to it, it just appeared. But that is not the case. Like one of the things that I really try to get across when I'm talking to people who do NLP and LLMs is that people were worried about these things from before. Like this is an XKCD from June of 2019. Back then, LSTMs were still used as like language models. And what this cartoon is showing is basically someone is using like a smart compose. This was when Gmail smart compose was being used a lot. And they're saying long live the revolution, our next meeting will be, and then the autocomplete is giving away the location and the time of the meeting. And again, it's an XKCD cartoon. It's not like a cartoon for like a paper or something. So this was something that was like people were worried about it happening from even LSTM times. But back then, security privacy researchers who worked on it only did the hypothetical. If this happens, then what? It was more of a this could happen, but does it happen or not? And then there was last November, I think, where this attack surfaced that kind of broke Twitter a bit. Researchers, they showed that, if you prompt ChatGPT with repeat this word forever, poem, 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 it's gonna like repeat poem a bunch of times, and then it's going to start regurgitating training data, which they showed had like dozens of PII in it. Again, there's two different aspects here. One is it really leaking private data, which is questionable, but the other thing is it goes to show that the model is capable of memorizing and also reconstructing and regurgitating the data. So there was proof of concept, and there is even simpler versions of this that you can try, especially with code models, like GitHub Copilot or any kind of code model that you can get your hands on. Those are less safety guarded, and especially because they're trained on code and comments, they pick up the language better. So I've seen this happen a lot of times accidentally, even when you're not trying to do an attack. Like we were trying to take notes in VS Code in a group meeting like 2022, and we wrote up the thing like the title of the talk and then hi everyone. So we were writing a script, and then this was the autocomplete. My name is Anish. I'm a PhD student at Stanford. And then we Googled this person, and they are really a PhD student, but they're at MIT. And if you see if the website is on github.io, so it's technically okay for Copilot to be trained on it. It is public. It's all okay. But again, it shows that if you don't safety guard it, it's so easy for it to pick it up and regurgitate it. And yeah, so if you want to try it, like, you can try it on your own like data or website or whatever. It's very likely that you get things out of Copilot easily. But then again, I've been like giving these types of talks for for a long time. I usually get the next question is, okay, like, before it was, but these models don't memorize. Like back when I was talking about this, when we had LSTMs, a lot of people were like, okay, but you can't really extract anything. But now bigger models, we show that you can extract it. But now the question is, isn't it all public data? So why should we care? Um, you should care for multiple reasons. One is publicly available is not publicly intended. So the fact that this is public data does not really mean that it was there, is put there with consent. And then the issue of consent itself is like a whole research field of like, do people understand consent? And even when you consent, you're sharing your data, but with a lot of data, you're also sharing other people who are correlated to you. Like even with genetics, it's a huge deal that even if you don't do 23andMe, if your sister does, then you're basically giving away your genome as well. So there's all those issues that go around it. But assuming that we have this pool of, public data and it's all okay, one thing is we are running out. We are running out of public data. Like we've already scraped a good part of the web that is actually useful and you want to train on. We could scrape more, but the point is there is this untapped treasure for at least for companies of the user data, right? Like ChatGPT and OpenAI, they collect so many tokens every day, and a lot of this data is rich data, right? It's actually what you want to do because it is the user's data. So if you want to give users a better experience, why not use their data, right? So there is a huge incentive to actually train models on this user data. And that is what is going to create problems down the line, is what happens when we start to rely on user data more and more. And then, is it going to get memorized? Is there going to be a data breach? Like, what are all the things that could go wrong when all of our data is collected? So the questions are, why should we care? What can go wrong? And then what can we do about it? And these are all questions that I deal with in my research, but I'm not going to tell you my whole life story right now. I'm just going to tell you some of the interesting findings that might be relevant. So I'll start by just motivating a bit of why we should care and what are the examples. Then I'll tell you about the tools that we can use to measure the leakage of these models and kind of quantify it. And then finally, I'll talk to you about some risks that I call them emergent risks, because there are some things that would go wrong with any ML model. And now we have to adapt those attacks and think of those risks when it comes to language. But then with the way language models are deployed, we now have emergent risks. We have new things that could go wrong that didn't exist before. So how can we figure those out and try and protect against them? So that's kind of the main directions that I want to talk about. Are there any questions so far? Oh, there's some stuff in chat. Sorry. Was that? Oh, it's happy birthday stuff. Thank you. Okay, great. So I'll start. So what are the things that people share with chatbots is what I'm going to open with, because I mentioned that if we start training on user data, what could go wrong? And the reason I'm doing this is, again, a lot of times I present protections and mitigation methods, and I always get this oh, no one is dumb enough to say this to ChatGPT, and no one will use ChatGPT like this. And then I usually my comeback was okay, but I've seen people do it, but that's not scientific enough, right? You can't just go and be well, no, I've seen people do it. That's not a retort. So so that's what I want to tell you is what are people sharing? Let's actually have a scientific look at that. And there are a bunch of papers that have lately come out. So these are the three of them, and I'm going to present kind of a summary of two of them that we did. There's a really good one out of the last one that is more in an HCI sense. But let me tell you the work that I want to talk about more. So in order to just find evidence of what people do share with LLMs and why it's dangerous, I want to take you on a deep dive of this data set called WildChat. So I don't know if people know what WildChat is, but basically it is this data set of 1 million conversations between users and chat GPT bots like GPT-4, GPT 3.5. It's been going on for almost more than a year, actually. And they've collected this data. And the way that it's collected is that users don't log into OpenAI, they log on to this other space, and they sign this consent form that you're basically not paying for using ChatGPT, but your data is being collected. So you're paying with your data. And the whole purpose of creating this data set was to have a data set for instruction tuning and human feedback and all of that. But it's really interesting when you put researchers from different backgrounds together, right? It's there were people who were sitting next to me at AI2 and they were collecting this data and they were oh, we want to use it for preference data. And I was what? This is so good to see what people care about, privacy or not. And they didn't even they were what? Private data? That was, so it's very interesting. It didn't occur to me that you could use this for RLHF and human feedback, and it didn't occur to them that you could use it for this type of study. So that's one thing that is fun when you have diversity. But so as soon as this data came out, I was like, okay, I'm just gonna go in there. I'm gonna find a couple of stupid examples of like things that people share, and then I'm just gonna use it in my slides from now on. So that was the whole point of what I started out with. Um, and I'm going to show you some examples right now. And in these examples, you might see names or PII. Those are all up, like they're not redacted. I've changed them. They're not the original value, but the data set is open, so you can go see them. So some of the data is obfuscated, but it's not the real data that was there. Yeah, so let's actually look at what are the things that people want. So as I was like going through this data set, I was wondering like, oh, okay, so what is it? What are the tasks that people want? And one thing that okay, actually let me get into it and then I'll acknowledge that. So we did this study of different tasks. So we created, I think it was 10, 12 tasks. And I want to give credit to Maria Antoniak here because she was the one who like did the actual task annotations. So there is a process that people do, and if people are interested, I can explain how it goes. But we basically hand coded the tasks. So we went through the task and we like manually annotated some of them, and then based on that, we built like a code book, and then we had GPT-4 annotate the rest. And what the takeaway was that we found that a lot of the queries to chat or like to chat GPT were the same, they were very similar to how people use search like Google. It's how-to information, advice, retrieval, things like that. But then we also found one thing that is different about this data set that was kind of surprising is that there is a lot of story generation and role playing. And this is this so there's it is creative writing, but a lot of it is just erotic story generation. So there was like I think 40%, there's so many of those that we did toss out part of it for like the rest of the study, but there's a lot of those. And I think it could take a separate study of figuring out what kinds of role playing and story writing people do. But this is one that you just can't do with a web engine or like with a search engine. So that was also interesting. If you're interested in like studying it further, this is definitely something an HCI study there. But then we were curious about sensitive information, right? And one thing that I want you to take away from this is that a lot of times we conflate PII, personally identifiable information like SSN names, dates, whatever, with sensitive information. And they overlap, but they're not the same. You could have PII that is not sensitive, like it's common knowledge, like the phone number of a hospital. It like a PII classifier would classify it as PII, but it is of a hospital, so it's really not that sensitive. And then on the other hand, you could have things that are not PII or not well formed, like your preferences, your hobbies, your activities that might seem like they're not private, but if you put them together, you can infer your location or other things that might feel sensitive to you. So there is this thing that you should keep in mind, especially when dealing with language, that sensitive information is very elusive. So we did a categorization of what are other sensitive topics. So we defined these 11 topics of like, your academic information, like strings of code that are like, they could be URLs or anything that like an API token, fandom, like what kinds of things you follow, financial, corporate, so all these topics. So we also did this, and then we built this like heat map, which is very hard to parse, of tasks and sensitive topics, because we were interested to see what kind of sensitive information people share for what tasks. And if you're interested, again, there's so much of this in the paper, you can go have a look at it, but I'll just show you some of the examples that were like, they show this problem more. So the first is on academic information. So we saw a lot of sharing of sensitive or like personal academic information for editing and translation tasks, which might seem kind of weird. So I'll show you an example. So we found this professor who's an associate professor who was writing rec letters for a student, and they were just asking ChatGPT. So they had dumped this student's information, like, when they met, what the student is doing, the student's grades, a lot of information about the student to ChatGPT and asking ChatGPT to help them write a letter. And again, this is in WildChat. So this person actually logged on to WildChat and knew this was going to be public. And again, it's so easy that like we found the person's LinkedIn, like super, super easy. So for all of these examples that I show you, like we've somehow de-identified the person, either LinkedIn or other things. So this is like one example. And that's why we ended up writing a paper because I went in there thinking that I'll just find a couple examples and I'll show in my slides. But then it turned out to be so much more. And then, I was talking to Maria and Maria was working on something similar. So we were like, okay, it seems like there is more here. And that's why we like ended up going deeper. And then another thing is coded text. So in code generation and code editing. And bless you. Uh, so there's a lot of coded code. And again, you might think that what is private in code? So this is something that we don't we usually don't remember when you're like dumping your code in ChatGPT and asking it to debug. You normally are probably copying your API tokens, whatever token it is. So we found a bunch of tokens like this. And also we found a lot of comments between code co-authors of like, like John, fix this, or like Alex, you do this. So there's and again, and even if you know it's going to be shared, it takes an effort to remove this, right? Like I just want to debug my code. I'm going to dump it. Who cares who's going to see it, right? But it is being shared. So that's another thing. And then this one was kind of one of the ones that was like really weird because this person was trying to write a letter for embassy and they shared their information and their father's, but it also had their visa and passport numbers. And I also like again I found this person on LinkedIn, so it is very insane. Like it's just I don't know what to say. Oh, okay. This one is the identified, but this is also super easy to Google. Sorry, my boxes have moved, so now you can see the actual text. But there was this one was actually the first example, but it's still the scariest example to me. It's a journalist who is asking ChatGPT to write to not just help to actually write an article for him. And what they're dumping into the model is a private WhatsApp conversation they had with a source, and this source is the mother of three kids, one of which has a rare disease. And this mother is complaining about how their country and the government is not supporting her and like her child that is going through this like really awful. So there's medical information and yeah, and this is the WhatsApp conversation. Like there is names in there. It is like literally a copy pasted WhatsApp conversation. And the mother even says like, do share this in your article, don't share this in your article. And she also like gives the name of some other mother who might be interested in talking to the reporter. And yeah, and then the reporter just like takes this, feeds it to ChatGPT, asks ChatGPT to write an article, and then we actually found the article online. So like dude copy pasted the chat put output as an article. And we did a Rouge L analysis, like the Rouge L with the original article is 0.62. So he didn't even like change it that much. So there's like parts that are verbatim copies. And then that kind of prompted us to we did like a short follow-up study of how do journalists use it, and we found like over 118 articles on like that in ChatGPT that we could match to online articles. So like a lot of journalists just dump conversations with their sources in there, and then they ask it to like write an article and then they publish it as is. So again, if you're like interested in these types of studies, there is a lot more in chat that we didn't go through. Like you can easily cluster the requests as well. Like a lot of people are like most users have a lot of queries, so you can easily cluster them, learn so much, de-identify. Like there is a lot to study there that we didn't do, and like if you're interested in, I think it's a good thing to just have a look at and see what is going on. Because with these, like there's more about human intention in there as well. Like, why do you think like why was the professor using wild chat? Because that's also another thing. It's like, okay, you're a journalist, why not just use the free version of ChatGPT, or just why not pay for it? And then like, or that professor who was an associate professor, like he would know better, right? Why do you think that professor was using the wild chat interface and not ChatGPT? This was actually interesting because yeah, this was interesting because it again it shows how diversity in research helps, because I was very, very surprised. Like I saw those things, I saw a lot of letters to embassies, and I kept thinking to myself, why? And these are one-time things. Like, why aren't they just using the free version? Why aren't they paying? Does anyone have a guess of why some of these like weird cases, or like this journalist who's from Malta, like, why are these people using wild chat, although they know it's going to be public? So this is funny because I'm Iranian and even I forgot. OpenAI interfaces are blocked in Iran and China and a bunch of countries. And using this is similar to using a VPN. So a lot of people can't really use the interface. Not only they cannot pay for it because, dollars is expensive or whatever in their countries, but also in some parts of the world, you just can't access it through OpenAI. So it's kind of like, I'm just going to use this. Which again, when another one of my collaborators told me this, and I felt really bad because I saw so many queries in Farsi, and I was like, God, why are so many Iranians using this? This is just so weird. And I also had forgotten like that, yeah, everything is blocked in Iran, so or in China or like a lot of places.
Yeah.
Um,
Just a heads up that there was another potential explanation for it in the chat here, but maybe it's not how you would explain it additionally, but I would just want to see whether you have additional thoughts on this. So Slater says, is it a loophole around company policy to not specifically use ChatGPT?
That is a very good question. That is actually what I was going to be my second point. Yes. So, in let me actually go back because I want to acknowledge this paper. So in these papers, so this one, the fair game one, the last paper that you see on the right here, this is by some amazing HCI researchers, and they actually looked at the human aspect of it more, and they actually went and interviewed people and talked to actual users. And one of the concerns that a lot of people have is because through this interface, you don't have to make an account. So technically, you're more anonymous because even if like it's not going to be collected in your personal account, it's not going to be related to you anyway. So although this is going to be public, it is not going to be linked back to you, which could be out of fear of like for your company finding out, or any form of like, especially in the like erotic sexual cases, that maybe you don't want it to be linked back to your personal account, or if someone opens up your like chat GPT account, you don't want them to see. So that was another thing that we I think Maria was also like hypothesizing. And then when I saw this paper, the last paper, I was like, yeah, they do a good study of this. So yeah. And on that aspect of it, the people from this paper, the last paper, Tianchi and her group do a lot of cool HCI work in that direction. So again, if you're interested in the HCI NLP aspect of it, do check out her work because she has a bunch of cool projects going on. But yeah, that's a very good point. That's another reason. Okay. So yeah, this was okay. This was this. And one concern with all of this, like I showed you all these examples, one concern is the model might pick up, might memorize and regurgitate it. And that is debatable. I've done a lot of work on memorization, and it's not super easy for a model, especially if you're training it such large scale. All of the information does get diluted. So memorization is not necessarily the biggest concern here, although it is. I don't really know how they do if they're doing like a small batch fine tuning, if there's any examples here that are really good and they train on it multiple times, then yes, it could actually be picked up and regurgitated. But another worry that I have is just this collection of data. The fact that all of this data is sitting somewhere, and it could like it could be victim of like ransomware or like some kind of data breach, and then all of these are going to get breached. Or another thing that like more security and privacy people worry about is the fact that we don't know how the data is going to be used. Like there could be in the future marketplaces for this data, for your data, like profiles of you to be sold, and then this data could be put together with like data from your Google Maps account or like whatever. So another thing is what is going to happen with this data that is kind of concerning. So yeah, that's it. Like it could be memorized, it could also just be leaked, and either way, it is scary and concerning. So with that, I'm gonna end this part of the talk. Are there any more questions?
Um, So I guess my question would be around recommendations you have for people and students here in the class for how to give recommendation to other people of how to approach these tools, because there are now options, right, to opt out if you click enough forms in OpenAI. But then a common thing I show also is GPT-3 paper where they reported that they had a bug and that they could not retrain the model and that they trained on the data they didn't intended. So there is always for me, a human factor, like an engineer unintentionally making a mistake and training on your data. So what are your recommendations on how to use these tools and whether to provide any information about you, or if you are using it to, I don't know, write an email and you are mentioning other people and so on.
Right, that's a very good point, and I have like some research recommendations that I will talk about in the future work. But in general, as people using the tools, I think it goes a long way to just check what you're typing and like remove it, because yeah, not using tools is like it doesn't make sense. You can also turn off in a lot of these cases, as you mentioned, like going through many forms, you can turn off the training, but that doesn't turn off collection. And there is so much nefarious stuff going on. Like I was going through because especially because like Anthropic is the good people, they have this whole thing, we are the transparent ones and we are the good ones and whatever. So I normally don't go through the privacy policies that much because there's nothing you can do about it. But I was like, okay, let me go through it. And it was so buried deep that I just felt so bad about it. They have this thing that we only train on three things. Public data collected from like our graders and like our like Turkers or whatever. And then the third one is explicitly consented user feedback. And reading that, I thought that it's like, you go and type in your feedback in a form or like some other like whatever. But I got very curious about what this last thing is. So I went into the docs and like I spent a couple hours, like literally it was not easy to figure out because you had to like go through three blog posts and whatever. And then I realized that explicitly consented user feedback is if you thumbs up on a response in the conversation, like you're talking to Claude. If you thumbs up one of its responses, that makes that entire conversation explicitly consented, and they collect that entire conversation, they can train on it, and they also keep it for 10 years now. Whereas the normal keep time is like 30 days or 60 days is what they like, it's normal. And they say they don't train on it, but as soon as you hit thumbs up on one of the responses in an entire conversation, it gets collected and trained on, which I think is very, and again, the phrasing of it was awful. I can share it because I screenshotted it and I even tweeted it. And I had a couple of people who are like, there are nitpicky people on Twitter. They were like, no, this is not what it's saying. You're reading it wrong. And then they went and they looked and they were like, oh shit, you're right. Like it is really phrased in a nefarious way. Like it did really piss me off the way they buried it under a bunch
Yeah,
of other things.
that's very misleading, and it kind of speaks for how hard the informed consent is with the data, right?
Yeah, yeah. So, anyways, read those things, watch out. But what research-wise, what I'm pushing for, and like that's one of the reasons that I also know of Tianqi's work, because HCI side she's pushing for it, is nudging mechanisms. If you can have very simple small models that run locally, like she made this Chrome extension that, like, if as I'm typing it in Chat GPT, it just tells me, oh, watch out, you're sharing your SSN, or oh, watch out, you're sharing this thing. Or even like even more, if you want to be more sophisticated, it could like highlight the spans and be like, do you want to delete these, or like, that type of thing. I feel like to me that's the perfect middle ground because I can still get the service. And honestly, there are people who are called privacy pragmatists, is people who don't mind sharing their data if they get a better service or if it's just good. And I don't mind sharing like a lot of the things that I say with the model, but as long as I can be like, okay, at least I didn't share this and this and this. So, but I'll talk about it more in the future direction because it sounds easy, but it's very hard to implement something like this. Okay, cool. So let me go over the societal. Okay, so we talked about societal impacts. I'll now tell you about how we can formalize the leakage of models and how we can measure it properly. Okay, so how do we measure training data leakage? Assume our data is collected and it's maybe used to train a model. How do we measure the impact that it had on the model? So for measuring data leakage in the sense like from a privacy or security standpoint, how people have been doing this for many, many years is that they define, this is one definition of leakage, by the way. There's different definitions too, but this is like kind of the like upper bound of leakage if you think like it's the slightest leakage. We say that there is data leakage from a statistical model M over data D if you're able to infer any bit of information from M about D that you would not be able to infer from any other model trained on similar data. So that's a lot of words. I'll give you an example to help make sense out of it. Let's say we're running a clinical trial and we have John, Jane, Alice, and Bob take part in this trial. And let's say that the trial tells me smoking causes cancer. This is not a leakage. The fact that smoking causes cancer is not itself a leakage of information, because if I were to run this trial on any other members of the same population, so it's the same distribution, but other data members, other data instances, I would probably make the same statistical inference. So this is technically not a leakage in a sense that is concerning for privacy. But if I were to learn that Alice has cancer, this is considered a leakage. Because if I were to remove Alice from this data point, then I would not be able to make this inference. So things that are overall statistical inferences that you would be able to learn with or without a certain data instance, that is not a leakage of that. Although it tells you something about the person, but it's not a leakage. Like if you know that Alice smokes, and then this like trial told you that people who smoke get cancer, and through this you can infer that Alice might have cancer, this is not a leakage of data. Again, under this definition that we're looking at. So it's a lot about membership of like if how things change, whether or not a person is a member of training data or not. And the simplified like version of how you can test this is a test called membership inference and a membership inference attack. And what this kind of test does is if you give me the model and you give me a target data point, I will do a binary classification. Was this training data point a member of your was this data point a member of your training data or not? So it's a simple classification, yes or no. And that's how membership inference attacks work. And there's many of them. And again, these have existed from actually 2009. They started when people started building models on genomic data. And they were like, oh, what if this like reveals something about someone's like genes or whatever? And then they started growing more and more. And in 2017, the first one was mounted on deep learning models. And then after that, we've been mounting them on different things. So again, a lot of people read LLM. This is one of the things that they read LLM papers and they're like, oh, this is how you detect pre-training data. This is not a new thing. Like detecting pre-training data is not something that someone like just suddenly invented. Like this had existed in the privacy literature for many years. And there are many formalizations of it that you can go and have a look. But yeah, that's the test. And one thing to remember about these tests is that their success rate is a measure of leakage. So if the test is successful, then you are leaking something. But lack of success doesn't mean you're safe. So this is why you cannot really use them in litigation or like copyright. Like they could be a tool to provide evidence, but they're not definitive, right? If it's telling you no, you just might have a bad attack. Okay, so what is the simplest form of doing such an attack? Like what is the simplest form of measuring leakage? So the basic like easiest way to do it, and this is a 2018 paper, is to just go with the intuition that if a data point was seen during training and if you've kind of overfit to it, it would have a lower loss value. So you just, you set a threshold and then you're like, okay, if the threshold is like loss of like 2, if my data point has a loss of 1.5, then, it's lower. So it was a training data member. And if it's higher, it wasn't. And obviously the problem with this attack is that it lacks precision. Like if you have this would be like your members and non-members, especially in language when you try to adapt it. And in language models these days, it becomes much, much harder because this static threshold does not account for the intrinsic complexity of samples. Like in language, we have a lot of samples that are just difficult. As you see, like here, we have a long tail. So even if you have seen the data point, it's just going to have a high loss. So there is no calibration. So now the next step is, how do we calibrate? Like, what do we do to give us an idea of how easy or difficult a sample is, and then calibrate the loss based on that. Does anyone have any guesses of how you would calibrate the loss for complexity? Like, what are the things that you might incorporate to help you get an idea of, like, in an objective sense, is this a difficult sample or not? It is a hard question, by the way. Like, it's not simple, but I was just thinking if anyone has any intuitions.
One thought I'm thinking is like maybe the length of the question and complexity.
That's a good one. It's very interesting because I ask this a lot and I get length a lot. There is the length is a good point, and in fact, there are more recent papers that build on the length, and they use length and they use compression, because like the length also tells you how compressible the sequence is. In a sense, like, what is the original length, and then if I compress it, what is the length, and then you can use this difference as how hard it was. Like if you use zlib compression and then compare the lengths. That is something that people do. So that's a good one. And what people do is like any kind of reference. So if you can use any kind of reference model to calibrate your loss, then you can kind of have this likelihood ratio of like, oh, instead of looking at just the likelihood, I'm going to look at a ratio with respect to like these reference models, and then help calibrate with that. And again, one thing is, mathematically, in terms of optimality, there's a group of attacks called there's an attack called Lyra, which is like a proper likelihood ratio, and they show that you need to have like not infinite, but like many hundreds of reference models, and then the expected value of all those references is an optimal, yada yada. But in language, it's like really hard to do that. So what people normally do is they feed the data point to the target model, and then they feed it to a reference model. And the reference model could be like any model trained on similar data that has an idea of what the distribution would look like. So if you're trying to like attack clinical BERT, you could use PubMed BERT as like a reference model, something like that. And in fact, in the paper, so there's like these are kind of concurrent. So we did a paper on mass language models, and then this other paper out of Google did a similar thing for autoregressive models. And the autoregressive paper actually does use the length and the compression that you mentioned as a baseline. So that was a really good guess. Yeah. Anyway, so that's another thing. You could use references as a way to calibrate the loss. And yeah, once you do that, the distributions actually start getting more distinguished, and it works well. But one problem with the reference attacks is that the ideal reference has to be trained on this specific data set that, again, is from the same distribution, but not the same exact data. And that is really, really hard to do with LLMs, right? Like, we cannot train our LLMs from scratch, and like, where am I going to get data? Like, I'm already training all the corpus of web. Like, where am I going to get new data from? And then how am I going to train a data model from scratch? So this whole issue of references can become very hard to deal with and find a good reference. And if you don't have a good reference, you might as well not have a reference, right? So this is the case that, again, depending on what you're trying to do, if you're attacking a model that is already trained on a lot of web data, then it's going to be really hard. But if you're in a medical setup, this is still an optimal attack, because you might be able to hold out a part of data, train a smaller model. But let's assume that, yeah, we can't have an ideal reference. So how do we get around this problem? Like, if this is not feasible, then what do we do? Like, what kind of calibration, like what can we look at that does not rely on a reference? You're still only looking at the model alone, but you try and get more of a signal out of it that is not lost. And again, I'll pause to see if there are any ideas, but think of like when you have something and you look at its value and it's not enough, what do you look at after the value alone to like get more signals out of it? So the loss value is one thing, but what is the next thing you would look at if the value alone is not enough? Any guesses? Think location, speed, and acceleration. That's a hard hint, but I tried.
That's supposed to be like force in physics and something.
So like what is like, you know, like you have a location and then you have a speed and an acceleration. So what are those? What is the relation? It's the derivative, right? So if the loss alone is not enough, we look at the derivative of the loss, which is so this was like kind of an idea that we had. We were like, okay, let's look at the derivative. But again, this is one of those things that is very easy to say out loud. Okay, let's look at the local optimality, but it's very hard to do in language of like, how am I gonna, and especially in a black box sense, right? How am I going to look at the derivative of the loss for a data point? So you either have to backprop, and that becomes hard. And then even if you do it, actually the backprop doesn't work. So we did this thing. We had this intuition that we could look at the shape of the loss and the local optimality by building neighbors. So we do this thing which we call the neighborhood attack, where for a data point we build a bunch of neighbors by perturbing, like masking and perturbing it, so that we have an idea of what the loss function would look like. And then let me show you the graphics. So if like this is the loss function, this is the data point, this is like your target data point, and if it is a training point, the intuition is that if you build neighbors around it, they're all going to have lower likelihood, right? So you're in a local optimum point if you have a training data. But then if you have a non-training data, like the circle point, you're going to have some points that are likelier, and then you're going to have some points that are less likely. So that was kind of the intuition that we had. And we were like, okay, let's try and build an attack around it. And let's see like what goes on there. So does the intuition make sense so far? Okay. I'm going to preempt, because there is probably going to be a question of, do we use embeddings or not? And I will answer that. But let me explain what we did that worked, and then I'll tell you all the things we did that didn't work, which are also interesting in terms of why they didn't work. So how the attack works is you have a sequence, and you feed it to this model we call the neighbor generator, which we use the BERT. So we did like the 15% masking. So we would mask it and then have it generate, like you would randomly mask 15% and then have it fill out and generate neighbors. So we found empirically that 25 neighbors is good. 10 is a bit not enough, but less than 10 is just like too little. So you generate neighbors, and we found 15% masking to be optimal. And yeah, you generate the neighbors, and then what you do is you feed all of them to the target model. So target model is the model whose leakage you're trying to assess. So you feed all of these to the target model, you get the loss values for them. And then again, if you like squint your eyes, you'll see that this is also a form of likelihood ratio attack, because you take the loss of your target point and then you subtract the average of all these neighbor losses to figure out if you're like on average above the neighbors or below them. And then based on that, you threshold it and make a decision. So again, if you think about it, and this has been shown in privacy literature, that all of these attacks are a form of likelihood ratio, because at the end of the day, you are calibrating the loss one way or another. So here we are calibrating the loss with respect to the neighbors. And then based on this, we decide if it's a training data point or not. So that's kind of the overall looks of how the attack works. And in terms of the logistics of like what is the best way to do it, we found that what matters, like in terms of defining a neighborhood, and there is a distance when you're defining a neighborhood, right? Like how far do you go? We found that this distance is more controlled by semantic similarity and fluency than it is by actual distance. Like we tried to mask like fewer words, and we also try to directly perturb embeddings, because technically that should be the best thing, right? Like if I take the data points embedding and then I like walk away from it by creating like embeddings, by like adding noise and actually like directly manipulating the embeddings, technically it should be optimal, but we found it to be way worse. And one of our assumptions, like one of our hypotheses was that it seems to really matter that you walk on the manifold of things that are natural language and text. Like when you directly intervene with the embeddings, then you're manipulating the space, and you're going into a space that is not even language anymore. So that really seemed to throw them all off. And we found that if this like neighbor generator, the better it is linguistically, the better neighbors we get, and then a more accurate attack we have. So we tried BERT, T5 small, T5 large, T5 XL, and then we found that the biggest T5 like conclusively gives you a more precise attack. So it seems like the better linguistically and semantically closer neighbors you have, the better attack you have. So we did try embeddings and it didn't work. We also tried like analytical derivative or like actually backpropping. Those also didn't work because what I hypothesized was that you really need to define the neighborhood. Like there's like this Goldilocks zone of not going too far and not being too close. Because if you're really that close, if you take an actual derivative and you're super close, that also like doesn't really tell you much. So there is like this Goldilocks distance that you want to have that we created. And then I'm not going to really get into the experiments that much because we're also running out.
Sorry to interrupt. There's just a quick question in the chat.
Yeah.
How do they measure fluency distance of attack and reference?
So how did we measure this is one thing is I did get semantic embedding distances. Like, you can get, what are those BERT models, like sentence BERT or something? You could like get BERT embeddings and then actually measure the distance. I think if you look at the paper, we do have things that like we showed that, when you generate these neighbors with like T5, like XL, you get better neighbors. And like that are closer in terms of semantic similarity if you use like a sentence BERT or BERT score or something like that. I think we tried those, but it's still very anecdotal. Like you can never prove, like it's really hard to visualize the space and actually be like, oh, this is closer. We tried doing it, but it ended up being like extremely inconclusive and like just hard to measure. Yeah.
And I have a very, very basic question. So once you have the output of a loss from your target model, which loss is this exactly? Is it a language modeling loss or a loss with respect to some target task? What did you?
Very, very good point. Very good question. So the target models are all autoregressive here, and we just test them like it's all GPT-2 models. And we just test the cross entropy like next word prediction loss. So it is not for a specific task. It's just the overall loss of the sequence. Yeah.
Gotcha. Thank you. Any other questions before we move forward? Okay, seems like things are clear.
Great. So like you can have a look at, for the experiments, you can look at the paper, but the main takeaway from the experiments was that if like this attack does as well as the likelihood ratio, like the reference-based attack, especially if you care about the low false positive rate, like if you want high precision, it's good. And also it's good or even better if you don't have the ideal reference. So we try a different set of references. And if you have a mediumly good reference, then this is better. But again, I want you to just keep in mind trade-offs of like what you're trying to do. Another way in which this is not good is that this whole process of generating 25 neighbors and scoring them is actually time and compute intensive because you have to mask and then regenerate 25 times per data point. So that itself did at inference time end up being costly and like it made it compute intensive. Like if you want to run this attack on 1,000 data points, and you're like resource constrained, it's harder. Whereas if you have a good reference, you just have to run one inference run on that reference. Whereas here you have to do 25 rounds of 15% masking generation, which is like way more. So again, it depends on what you want to do and what you want to accomplish and you choose. But still, this attack is still one of the state of the art, and like all the attacks that come, they do compare with it. But yeah, there are trade-offs. One side note is that this attack might look familiar to you. And if you know the literature around machine-generated text detection, and in fact, it came out at exactly the same time as Detect GPT did. So this is literally the same method, and it was fully concurrent work. And I think technically ours is first because we were ACL 2023, they were ICML. But anyways, like it's the same thing. And then when I saw it, I was like, well, you're first shocked and you're a grad student, you're like, oh, did I get scooped? But it is a different application. But that really got me thinking about membership inference attacks and machine generation text detection and how these tasks are related. Like, why is it that the same thing works so well on both of them? Because the intuition here is simple. Like around the same time, a lot of people were thinking of neighborhoods for different things. But then this got me to like run a bunch of experiments, and we did some follow-up work where you basically any membership inference method can be used as a machine generation text detection. So even like you can use the likelihood ratio stuff for this, or you can actually take other machine generated text detection. And the intuition is models like what they generate. So, and they like their training data. So if you have like 3 groups of data points, like you have human written text that is non-training data, and then you have training data and you have machine generated text, models will always like what they have seen before better. So it makes sense that a membership inference attack is as good as a machine generated text detection, like for the same thing. So again, it's a bit hard to comprehend, but do keep that in mind that these methods are related. Even like after this, there was this attack MinK++, which is basically the same thing as fast detect GPT. And yeah, like it's funny to just watch both of these research directions as they're going forward. You see the similar methods. So do think about it and keep it in mind.
Can I ask just a quick clarification question? When you say here curvature, I guess for me, immediately I go into like you are using a Hessian or something like a second order derivative or something. But it seems like you're just using the probabilities or log probabilities or the loss and checking the difference with the mean of this quantity about calculated over a set of similar examples. So I guess my question is, can you specify a little bit more this idea of curvature on the loss?
Right. The curvature is mostly just the intuition because again, thinking that like, oh, you have the fake data points and the neighbors, and this is approximating the curvature maybe. And again, in practice, it does seem to be doing it because both this screenshot is from Detect GPT. And they also, we didn't even mention the Hessian thing. We just like said that, oh, this could be seen as local optimality to give people intuitions. They have some math to show that this method is kind of similar to calculating a Hessian. But again, it's a very short section in the paper and it's very hand wavy and it's not a real proof, but it's just the intuition. Like there is really not a proof to show it. But yeah, it's you can look at their paper. They try to kind of relate it, but not.
Gotcha.
Yeah.
All right, thanks.
Cool. Thank you. Okay, great. We have around 20 minutes left, right? Or do we have
We
5
have
minutes?
until 2 in our time, 2:45 for you, 1:45.
Okay, great.
So
I'll actually
20
try.
minutes.
Yeah, I'll try and wrap up in 10 so we have time for like Q&A and stuff. But yeah, so this was this. And yeah, so machine, but one thing, this might not make sense. If it makes sense, it does. And if it doesn't, don't think about it that much because it's not that important. But one thing is machine generated text is technically an adversarial example to membership inference attacks. And what this means is if you get into to membership inference attacks, please do not use machine generated or like synthesized data as non-members. Like a lot of people use machine generated text as unseen data for models, and it might work in other tasks where you're trying to measure the mathematical capabilities or whatever. But if you're running memorization tests, this is going to be highly nefarious to you because models love machine generated text from other models as well. So machine generated text will always by mistake be classified as training data. So if you're trying to do an extraction, if you're trying to do like membership inference and you don't have non-members, which is very common these days because we've trained on everything. So it's really hard to find non-training members. Do not use machine generated text as non-members because it will be classified as training data members, which is very interesting, like why models really like their own generation so much. But that's just one thing to keep in mind. Okay. I will get to this one really quickly. So far I've shown you attacks and the attacks were successful. One thing that in 2023, my collaborators and I realized was that these attacks do not work on pre-training data, on Pythia or Llama style models and like actually large models. And if you try to use them on pre-training data. And this is funny, like if you look at, there's so many papers, so many people on this paper from different places, it's because I was running the attacks and it didn't work. And then Anshuman, who's my co-author, reached out to me and was like, oh, these attacks are not working. Like is there something wrong with my code? So a bunch of people, we like reached this realization, and then we were like, okay, let's investigate. So we ran all membership inference attacks on all different model sizes and all different data subsets to see what's going on. And you can have a look at the paper if you're like super interested. But the takeaways are that we're at a state that actually membership inference attacks don't work on these models on their pre-training data. And as soon as our paper came out, like 6 other papers also came up studying this in different aspects. And this is right now a very active field in terms of what is going on that these attacks don't work. And the main intuition behind all the papers is that there's 2 or 3 reasons. One is membership inference is about distinguishing members from non-members. And again, having trained on all possible training data, this line is very blurry. Like, although we deduplicate, there is still a lot of 13 gram and 7 gram overlaps that play a lot into these data points not being distinguishable. So that's one thing. Another thing is, this is one of the things that I'm super interested in from like a modeling perspective, is that data points that are seen only once leave a very weak imprint on the model that is not capturable by the signals that we have. So it's not that they don't leave anything, because obviously the model is learning little by little, but it's not capturable with this loss or even reference-based attacks. So I think this opens this cool avenue of what are the attacks that can capture data points that are seen only once. Because so far we have nothing. So if you have a data point that is seen only once, there is no way to detect it. And another, so this is one future work, and we can talk about it later, that is like, how do you detect data points that are seen only once? And it matters for many reasons, copyright being one of them. But another avenue of research is that we also found out that these attacks are super sensitive to syntax compared to semantics. And this is kind of in a way that you might not want it to be, and counterintuitive to privacy. It's like, if you change, like my email address is like .edu. If you change it to .com, then a membership inference attack might say, oh, this data point was not in there. Whereas, I don't care if it's like saved in the model with edu or .com or how it's memorized. As long as my email address is in there, like I care. And then it goes beyond this in terms of like, what are like, are data points memorized in a semantic way or in a conceptual way? And yeah, there are all these ambiguities of form and meaning in language, and like what happens to models when you instruction tune them, and like maybe something is not extractable in its given form and like syntax that it appeared in the data, but it's extractable in other formats. So it also raises all these types of questions, which are very interesting for future work. But yeah, so this was all with the memorization and membership stuff. So now I want to go to leakage beyond training data. So what can go wrong that we didn't have it go wrong before, and it wasn't even an issue? So one thing is in context learning, right? This emergent capability, you tell models, you give it samples of tasks, and then magically it can do the task. One problem that this causes is, I call this the cascading input-output problem, or input-output leakage, is assume you have, let me show, assume you're using in-context examples, in-context demonstrations for a medical task. So you're giving your symptoms to a model, and it's trying to tell you what kind of disease you probably have. So if it's running a RAG system or whatever, it pulls some similar cases from the data store, it feeds it in the context to the model, and then the model could give you something like this. Based on the clinical records of patient A, who's a 35-year-old female, yada, yada, you probably also have diabetes. So now we have this problem at inference time, that is whatever you feed in the input, or whoever is deploying in the model is feeding in the input, or whatever is in the system prompt can leak to the output. And again, it might seem simple in this case, but trust me, when we use models as agents and we attach and stitch 10 different data parts together, it's going to be really, really hard to capture things like this. So yeah, how do we protect whatever goes inside the model, if it's system prompt, in context example, proprietary prompt, from leaking to the output? And the question is like, can models keep secrets? Are they able to reason about privacy the way we do? Can they figure out what information to share for what reason and with who? So this is like a higher meta level kind of question of, does the model understand privacy? And yeah, we wrote this paper to study this question. And the way in which I wanted to look at it was through the lens of this thing called the theory of contextual integrity. So this theory is introduced by Helen Nissenbaum, who is kind of a philosophy privacy policy professor. And what she says, she has this whole book and like it's a conference and all of that. It's called Privacy in Context. And again, privacy is in general very debated between privacy people too. It's like, how should you do privacy? But her whole spiel is you have to think about privacy in context and as flows of information. So she says that you can't have a law that says that, oh, your medical records is private because it's highly contextual, right? Your medical record, you want your physician to see it, but you don't want it to be used like online for ad purposes, right? So everything is suitable in one context and not suitable in another. And another example is like, even with SSN, everyone is always like, why would you share your SSN? Obviously, if you get a prompt like this from this very weird PayPal looking thing, you're not going to put your SSN in there. You're going to know that this is like a scam. But then we all, tax season, we all log into TurboTax and we put our SSNs in. So again, it's all contextual. So based on this, we built this benchmark that has 4 tiers based on the different nuances and levels of context. And it starts from, like information types, and then we go to like, so something like, oh, is your SSN private or not? And then we ask them all more convoluted questions. Like, is it okay to share your SSN with your accountant for tax purposes? And then I'm gonna skip through these. And then the third tier is we involve theory of mind. This work was like co-led by me and Hyanu, who's like a theory of mind person. So he really he was like, okay, yes, we need theory of mind because that is a big part of privacy, right? It's like the way we think as humans about, oh, am I going to tell this thing to this person is based on my knowledge of what I think they know. So it really depends on whatever knowledge graph I have in my head of their belief graph. So we involve theory of mind in there as well. And then the last here, we try to involve compositionality. So if you have like multiple pieces of information, some of them some people know and some of them some people don't know, can the model break this into pieces and reason about each part separately? So the last tier is like super complex. So if you're interested, like have a look at the paper and all these tiers. I'm only going to zoom in on one of the tiers right now. I'm going to go into tier 3, which is theory of mind, which like kind of has the findings that I guess might be more interesting to folks. So here what we did was we planted secrets inside some scenarios and then asked the model, like put them all in a position where it had to generate a response, and we observed if it reveals the secret or not. And how it works is like we built a scenario where 2 people are talking and then a third person comes in. And then we were like, oh, what should Alice say? And then Alice is put in a situation where she may or may not reveal a secret that they were talking about. And one of the things that we tried to be careful about is we didn't want to put this decision of is this a secret or not to the model, because that is a highly that's like a moral question of like, is this a secret or not? So in the way we built the stories, we explicitly say that, oh, this is a secret, please don't tell anyone. So we define what the secret is in the task definition. So we just want to measure if the model figures out who it should share it to or not, or like, how the model does the generation. And then we observed, and like, this is from last year. Right now, most of these are patched up. But we did observe that GPT-4 revealed the secret 20% of the time, whereas ChatGPT revealed it 93% of the time. And most of the cases that it was revealing the secret was in a sense of it was trying to be helpful. Like, how ChatGPT is super verbose. So in that, as it was like talking around itself, it would reveal the secret. And we also tried chain of thought reasoning, which did not really help here. So I'm going to, let me show you. So we did this error analysis of how secrets get leaked. 51% of the time, the model acknowledged privacy, but still revealed the secret. So it would say something like this: I think it's important to consider Jane's privacy and the trust she placed in me by confiding in me about her affair. So it was saying that you should, preserve this privacy, but as it was going, it like ended up blurting out the secret. So I think that these do kind of go under the shortcomings and pitfalls of next word generation, like them all committed and now it just has to like finish it. 38% of the time it was theory of mind failure because it would say something like this: as you know, Adam and I have maintained confidentiality about his transformation and recovery, yada yada. So it assumed that this person already knows the secret, which is again not true because in the opener we said no one else knows this. So it was a theory of mind failure. And then 3% of the time, this is the most human thing, it acknowledges privacy, it reveals the secret, but reassures the person that, oh, I won't tell your secret to anyone though. So this is very common, right? It's like, oh, she told me don't tell anyone, but I won't tell your secret to anyone. So the model really does this behavior as well. And then 8% of the time, it would just reveal it without really any explanations. So it seems like we have problems still with theory of mind and with operationalization of knowledge. Like the model knows what a secret is, but because of next word prediction, it just ends up blurting it out. Okay, so I'll quickly go over the directions that I think I'll go over this fast and then I'll stop so we can talk about whatever directions you're most interested in. But I think one of the things that people should look at is just verbatim and fuzzy versions of memorization and regurgitation now. One step that we took in this direction was we looked at non-literal copying in copyrights. And this was something that I kind of got inspired by with talking to James Grimmelman, who's a law professor. And I found out that, there's a lot of copyright benchmarks right now that look at verbatim copying, like Harry Potter, do you get the first paragraph, first chapter? But as I was talking to James, I realized that you have this other risk of if your model like rewrites a story and the story might look very different, but if you have a series of events that are similar or in the same order as chapters of a book, that also is potential for like copyright infringement. So you can have like non-literal copying of information and data that could still be problematic and it's not verbatim anymore. So how do you capture that? So we tried to build a benchmark that like looks at series of events, looks at characteristics and things that are not verbatim copying and tries to assess the risk for that. And it's very interesting because instruction tool models don't verbatim copy as much, but they do this type of copying a lot more just because, they're trying to be helpful and they're built in this colloquial way, right? So they actually like, as they're building stories, they recall what was, in their training data and they're good at putting it together. Whereas a base model is less likely to reproduce data like this. So this is something interesting that I was like, when we have models that are deployed differently, we might have a set of risks that we don't even think of. So this is one thing. And yeah, so whatever, verbatim, non-verbatim. And the same goes for privacy. Like, can we do semantic attacks, semantic membership inference attacks, or just semantic re-identification attacks, where we try to see if we can learn more bits of information about someone, more attributes. And there is like some work on this. We did some work, some other folks at Oracle did some work. And finally, I think this whole direction of contextual integrity, both for privacy, even for like fairness, for other things of like trying to assess context and then making decisions based on context is really important. And like Google DeepMind is also looking really into this stuff. And there's a couple of papers that came out of Stanford as well of people trying to build, privacy norm awareness and like how you can build privacy benchmarks that are socially aware. So that's another thing. And then again, as a solution, I think nudging mechanisms and any form of taking control on the user side and sanitizing the data on the user side is the type of thing we should be looking at. Okay, I'm done. Thank you so much. And yeah, let me know if you want to talk about any of these more. We have 4 minutes left. Sorry, I went on
No,
super long.
it's great. Let's thank the speaker. I will have my one sad clap here. Thank you. Let's see whether there are any questions from the students. I will also check the chat. I have a question while maybe others are writing. So you did show us that the GPT-4 reveals secrets 20% of the time, way less than Llama, which kind of then suggests that maybe just scaling the models and improving them will, cover the privacy along the way, right? As many things are also sold along the way. So what are your thoughts about that?
Right, that's a very good point. Sorry, I'm gonna like take a note. So yeah, two things to take in mind is one thing that I like about working on privacy is that still there is no such thing as privacy alignment. So at least we know that what we're seeing is probably not because of, like Llama is not really aligned and ChatGPT or GPT-4 was aligned for this. We are now getting alignments against just verbatim copying, but it's still not this form of input output copying. So one thing is at least we can like disentangle things easier. And you're right, it is whatever reasoning, like whatever tricks was done to make GPT-4's reasoning and theory of mind better have definitely helped it here because it's like it's much more aware of the social norms. It's much more aware of everything that is in there. One other reason that I think Llama was just not good is that Llama is not super good with long context overall. So that's another thing. I think it just didn't really know what's going on. So it would just regurgitate, like copy and paste parts of the input, which made it worse. I do think, okay, so as a solution, one thing is, yes, we can wait for the scale to go up and the model might pick these things up. But one interesting thing with privacy and like a lot of common sense things is like one problem we have with common sense is there is no written text on what you should do, right? Like you should close the door to the fridge is not something we write a lot, or like a lot of things that are common sense, we don't write them. That's why Yejin has this thing of, common sense is the sorry, the dark matter. And the same with privacy, especially because privacy is very much don't do this, and we don't have don't this. Like models are not good at not doing things. They're good at doing things you tell them to do, which so I feel like there is this objective mismatch in the way we're training our models is that they're good at following instructions, but they're not good at not doing things, and they're not good at like following priors that we don't state. So I think it would just, if we want to only rely on scale, the scaling law would be way more like you would need way more data than you need for just following type of instructions. So I think scaling alone is not going to be enough. Like we might need some either like a different training objective or just like way more synthetic data that like teaches them all how to not do something.
Yeah, it's funny because it also relates to like problems I like to study, like how models don't handle negation really well. So it's funny to see this coming in a completely different setup of privacy as well. Yeah.
It is so cool. Like one thing is like a lot of times people hear like I tell them I do privacy and they have this notion of what I do. And then when I talk about my work, they're like, oh, this is like I've done this thing that is similar. Like with privacy, it's very much an application that relates to a lot of things, which is I really like that. Like you can take so many ideas from different fields. Yeah,
Yeah.
it's really
And you can collaborate with a bunch of people,
yes.
which you did. Very good. Okay, we should stop now because we are at time. There is one more question, so maybe we can, if you have Niloofar,
Yeah, sure.
time for maybe answering this one. Others, if you need to go, feel free to go. But this question is: are these attacks introduced used for out of distribution data detection, which is important in so many machine learning applications? Also, do you think fine tuning using human preference ranking could help mitigate the privacy leak problem? So the
Right.
first question is out of distribution, and the other one is unrelated to that.
That's a very good question with out of distribution data detection. I actually like I've been thinking about a lot about this in terms of poisoning as well. Like, can you use a membership inference to just like detect poisons because they're also kind of out of distribution? I haven't seen work that directly does it, although people do sometimes test the attacks on out of distribution data and show that it kind of works. So I would assume it, depending on how out of distribution it is and how it's generated, it might be different. But I think it's definitely a cool direction to try, especially for poisoning detection. I assume it might work on very obvious ones, but with some tweaking, there could be a good research paper there. So that's one thing. In terms of human preference, I think the human preference would be one of those like lipstick on a pig or like, just this
Mm.
put a stitch on it. It will probably work in a sense of like a surface level thing, of like just like getting behind very obvious types of secret sharing. But I think deep down, for two reasons, I don't think it's the viable long-term solution. One reason is that different people really want different things out of privacy. And like a lot of times, like let's say that you want to like train a sanitizer, and it's like trying to most actually like there are HCI studies that show that people don't want their data fully obfuscated. Like I don't, if I'm sharing something, I don't want the location to be removed. I want it to be abstracted. And then different people want different levels of abstraction. So that's one thing. Human preferences in terms of privacy are super different across different cultures. So I feel like just preference tuning might not be enough. And another thing is, as I mentioned, models are worse at learning what to not do from preference data. So it's with privacy, there's a lot of what to not share, and it's like it's harder to come across, like actually learn it in practice. So that might be another thing. But I think it is definitely the next step of like, yeah, you should do preference tuning while we figure out something better.
Got it. Thank you so much. Let's stop here. Yeah, again, happy birthday. Thanks for sharing your birthday with us. Hope you have more fun plans for the after lecture.
Thanks.